Well, for assignment 6, I'm just going to do the last 3 questions, numbers 7, 8 and 9. I think you should be able to do the first 6 on your own and check it on your own or with other students. So in number 7, we have to negate statements and put them in positive form. Part A was for all x in n, there is a y in n, x plus y equals 1. The negation for that is, and I think you'll get the same answer as I do if you get it right, there is an x in n, such for all y in n, x plus y is not equal to 1. You could have written that last part as not x plus y equals 1 if you like. That's equally correct. I've just used this way of writing it. Okay, and in this one, for all x greater than 0, there is a y less than 0, x plus y equals 0. The negation of that in positive form is there is an x greater than 0, and it's greater than 0. Okay. For all y less than 0, these don't change around. They stay the same way because these simply tell us what x's and y's we're looking at. And we get x plus y not equal to 0 here. Okay, for part C, there is an x such that for all epsilon greater than 0, negative epsilon less than x less than epsilon. And when you negate that, you get for all x, there is an epsilon greater than 0. And in this case, you're going to have to sort of split this into two. One of two things. If x is not between negative epsilon and plus epsilon, then either x is less than or equal to negative epsilon, or x is greater than or equal to epsilon. I didn't put parentheses around either of these. I mean, I could have done if I wanted to be ultra clear, but this takes precedence over the logical operations. Arithmetic expressions or inequalities and so forth take precedence over logical connectives, because these are connectives. They connect statements about mathematics. And this is a statement about mathematics, and that's a statement about mathematics. But if you wanted, you could have put parentheses around that, and you could have put parentheses around that. That would have been another way of doing it. Moving on to the last part, for all x in n, for all y in n, there's a z in n, x plus y equals z squared. We're not talking about whether these are true or whatever, we're just writing them down and negating them. So you get exist an x in n, exists a y in n, for all z in n, and I've just written this again, x plus y not equal to z squared. You could simply put a negation sign in front of that expression. Okay, well that's number 7. It's fairly straightforward. Let's move on to number 8. Question 8 is our old friend Abraham Lincoln, and this famous statement of his, or allegedly famous statement of his. And we need to negate that famous sentence. So let's let fxt mean you can fool person p at time t. And then his statement is this one. You can fool all of the people some of the time. There are some times when you can fool everybody. You can fool some of the people all of the time. So there are some people that can be fooled for at all times. But you cannot fool all of the people all of the time. Okay, let's just mechanically go through and negate that, looking at the formalism. And then we'll try to interpret the answer and express the answer in terms of English. Okay, so negate exists, it becomes for all. When it for all, it becomes exists. FPT becomes not FPT. Okay, conjunction becomes disjunction. Again, I'm not putting these in parentheses, and I'm not going to do it here because this is a whole. The quantifiers bind in; they're very tight binding. And then we have disjunction, conjunction here, and then disjunctions here. They're less tightly binding. So looking at this one, the exist becomes for all becomes exist. We get a negation. Conjunction becomes disjunction, and the negation here just disappears. So I've got a positive statement. Okay, so in terms of the formalism, this is fairly routine. In fact, this is such a routine thing that this is essentially algorithmic. I just went through and applied the patterns, the rules that I've observed happening. The interesting part of this, I think, and you weren't asked to do it, but let's do this. Let's see how we can express this in English language. And we're not going to get something quite as nice as this, I don't think, because we need to try and to avoid ambiguity as much as possible. So the first part would be, the best I can think of at the moment is, let's see, at any time there is someone you can't fool. And, whoops, or, because we've negated, or, okay, let's have a look at this one. Yeah, I can't really think of anything better than to say the following. For every person you can't always fool them. Well, you might be able to say, well, no, I think if you try and swap it round, you run into sort of American melanoma type problems. So to try and avoid that, I think I would want to write it this way. And then the final clause, well, that's easy, of course. That's just say, you can fool all the people all the time. Okay, I'm moderately happy with that. You might have different opinions on the best way to write them, but number 2 is a bit ugly, but I'm not sure we can make a better job of that one. Okay. In any case, we've negated the thing, and this was nice and clean. Okay, now let's look at number 9. Well, number 9 involves one of the most important and most famous, some might say infamous, formulas of advanced mathematics, of university level mathematics. It's this definition when students entering university to study mathematics for a math major. It's this definition that usually causes them the most problems during their first year. In fact, I think it's this definition that probably is responsible for more math majors giving up mathematics in their first year at university than anything else. It's a really tricky thing to understand, as many of you noticed, and I've seen from discussions on the forum. Figuring this out is really hard. This was hundreds of years of effort, starting with the invention of the calculus by Newton and Leibniz in the 17th century. It took a long time, several hundred years before mathematicians were able to figure out the notion of continuity and come up with this definition. This was late 19th century that this was done, and it was a tricky thing. Negating it is relatively straightforward, actually, because we've got rules for doing them, and so when you negate it, what you get is that the for all becomes exists, and it's still a greater than. We're still talking about positive numbers, epsilon. The exist becomes a for all. The for all becomes an exists. And then there's a bunch of stuff that's in a bracket here. This is a conditional, an implication, and so when you negate it, you get the antecedent conjoined with the negation of the consequent. So here's the antecedent. Again, I haven't put parentheses around that because this is a mathematical statement, and that takes precedence over the conjunction or disjunction. These are just connectives. They're operators that bring things together. So that's a piece on its own, that guy, conjoined with the negation of this guy. Okay, and the negation of it being less than epsilon is it greater than or equal to epsilon. Okay, so that's the negation. And that's relatively mechanical to do that, so long as you sort of pay attention to preserving things that need to be preserved, changing for alls to exist, and negating a conditional. The interesting question is, what on earth does this thing mean? You can read it through, as I just did, for all epsilon greater than 0, there's a delta greater than 0, such that for all x, yada, yada, yada. But what does it mean? Well, this is capturing in a symbolic language, in an algebraic formalism, it's capturing something geometric. So let's see what it's capturing. Let's look at the original definition of continuity. It's about functions. So let's look at a function this way. I'll draw the rail line vertically. This is the rail line. And then I'm going to draw the rail line vertically here. So this is the rail line. Instead of writing it horizontally as we usually do, I'm going to write it horizontally. And the function f is going to take numbers here to numbers here. Okay, so somewhere here we've got a. F applies to that. And it gives me f of a. Okay. Now we're trying to capture the notion of continuity at a. That means when we go slightly to the left or right of a, and left or right is up and down the way I've represented it, then the numbers don't sort of have a discontinuity. And the way to capture that, it turns out, and the chances are very, very high that you're not going to follow this the first time. It's going to take you weeks if you need to master this. But here's what this formula says. It says the epsilons are going to work on here. It says let's take an epsilon here. And let's look at f of a plus epsilon and f of a minus epsilon. So I'm going to take an epsilon interval around f of a. And what this definition says is that given an epsilon in one of these intervals, I can find a delta. So here's a plus delta and a minus delta. So starting with an epsilon, which gives me an interval here, for any one of those, I can find a delta which gives me an interval here, such that, now let's look at this, any x in this region, because this says that x is within delta of a, so any x in this interval gets sent to an image f of x in here. So it's saying, in order to make sure that all the values of the function are in this interval, I can find an interval around a such that they're all sent into here. So if I want to hit the target, imagine this as hitting the target, like throwing darts at a dartboard. If I want to hit the target within a specified accuracy of f of a, I can always do it by starting out within an interval of a. So to get within a given interval around f of a, I can always find an interval around a that does it. So everything from here gets sent into here. And if you think about it long enough, you realize that what that means is that the function is continuous at a. There's no jumps. And to try and understand that, let's look at what this guy means in terms of a diagram. I'll do the same thing again. I'll draw the rail line, and I'll draw the rail line, and here's a, and here's f of a. Now the negation says there is some epsilon. In the previous case, this was happening for all epsilons. You could find a delta. In this case, there's a fixed epsilon that we can find, and we look at the interval around there, f of a minus epsilon. Okay. What it says is that there is an epsilon such that no matter what you take here, no matter which one you take here we found one of these guys. We said take any interval here, we can find an interval here. Here we're saying there is an interval here for some epsilon, such that no matter what delta we take here, no matter how small you make this delta, no matter how close you here, that was a point that gets sent to that, you can always find a point in here that gets sent outside of there. Maybe sent that way, maybe sent that way. So there's some epsilon here that no matter what you do here, no matter how close you are to A, something gets sent out here. In other words, there are points really, really, really close to A that get sent outside this region. So there's no way that you can get all points in here. A gets sent to that, but arbitrarily close to A, there are points that get sent away. So there's a discontinuity, because only A gets sent close to A. When you get, well, some of the points may be, but no matter how close you get to A, you'll find points that are sent further away. So that's a discontinuity. Things jump. There's a sort of jump from there to things here or here. Now, the chances are high that if this is the first time you've seen this, that explanation is going to be hard to follow. This is really difficult to understand. This is extremely hard. And the goal of this course actually isn't for you to understand this. The goal of this course is to give you the machinery so that you're now able to take a whole semester course on real analysis during which you should be able to understand that. So I wouldn't worry too much if you can't understand this. The point is, if you could understand the first part and understand how to deal with the formalism, you now have the machinery you need to understand this very deep conceptual definition from within mathematics. Okay, and to have reached that stage in 4 weeks, I think is pretty remarkable. The hard part is to come, and for those of you that want to go on and study more mathematics, sooner or later, and hopefully sooner, you're going to need to master this definition and what it means. Okie dokie. Well, as far as we're concerned, we're done with this one.